before we start.
Good afternoon, everybody. My name is Dr. Julie Wall, and I'm a reader in computer science at the University of East London. I am delighted to be participating in this virtual summit on AI and insurance. During this session, I am going to talk to you about the research we are working on for detecting fraud in insurance claims calls. And for this, we use deep learning and machine learning. And I will be presenting how we develop these techniques in an explainable way. This research is being carried out in partnership with the companies Intelligent Voice and Strenus, both based in London, and we are funded by Innovate UK. We are working on the development of an explainable pipeline that will identify and justify the behavioural elements of a fraudulent claim during a telephone report of an insured loss. Our project team across all partners consists of machine learning researchers and deep learning researchers. We have data scientists, linguistics experts, and expert investigative interviewers. So how are we going to achieve this aim of analysing the behavioural features of speech for the detection of deception, especially in the insurance space? So we have curated a robust set of linguistic markers and their corresponding trigger terms that potentially indicate deception in a conversation. And using statistical measures and both machine and deep learning approaches, the detection of these linguistic markers in the correct context is being investigated. And we're also evaluating our development models with a variety of relevant data sets. Some of these data sets have been expertly created in lab conditions, while others, which are more meaningful ones, are sourced from real-world telephone conversations in the relevant domain. So we've been looking at calls between agents and claimants in the insurance space. The explainable pipeline means that the output of the decision-making element of our system will provide transparent decision explainability, and this enables us to overcome the black box challenge of traditional AI systems. So machine and deep learning have empowered the technological industry to solve many complex problems, some of which were not so easy in the past. And we've got examples including nowadays we're researching self-driving vehicles which slow down as they approach pedestrian crossings. We consider ATMs which can reject a counterfeit banknote. We all have smartphone apps which can give instant translation of foreign street signs. So all of these applications and models and systems are being developed using machine learning and deep learning to really help our society, help us with these very useful applications. But the use of machine and deep learning has also raised some serious issues. One of the most important issues raised is the explainability of a model. That's the explainability. How is it actually making the decision? And if we consider a recent case from 2018 where a car in an autonomous mode crashed and hit a woman, causing her death, we have to ask, who is actually accountable in this matter? And could this accident actually have been prevented? Well, could the development of, if the model had been developed in a different way, could the model have produced a different outcome? So let's look at some more examples in the following slides. Here we have the infamous tank example. So this anecdote may not be truly authentic, but it has an air of believability about it. In summary, the US Army trained a program to differentiate American tanks from Russian tanks, and they produced a model with 100% accuracy. Now that alone is suspicious to me, but only later did the analysts realise that the American tanks had been photographed on a sunny day and the Russian tanks had been photographed on a cloudy day. So the computer model had actually learned to detect brightness. And the military were now the proud owner of a multi-million-dollar mainframe computer that could tell whether it was sunny or not. Not really what they set out to achieve. And this is what happens sometimes when we have an AI system that is a black box. We don't always understand why the system is producing the output. Another infamous example is that of a classifier trained to recognize wolves from husky dogs. So all the pictures of the wolves had snow in the background, and the huskies did not. And it turned out again that the trained model was basing its decision solely on the presence of snow in the background and was not actually making its decision based on the individual features of the husky or the wolf. So in the image on the left, you can see a husky dog, which the model actually classified as a wolf. And in the image on the right, you can see the part of the image responsible for that incorrect decision. And the part of the image was the snow. So the model was seeing the whole image, but it was only extracting what it thought was the most important part, which was the snow in the background, leading to these incorrect classifications. So being able to drill down into what part of the image is causing the classification is a form of explainability. And this is a very useful technique for analysing the decision-making output of an AI model. There are other life and death decision support AI systems in operation nowadays, for which decisions are life and death critical. Some examples of this include image classification of military targets, deep neural networks, or to be specific, convolutional neural networks for medical diagnosis support. For example, the Johns Hopkins system, which is very successful but needs explainability. And the irony is that it was actually developed to save lives and also reduce malpractice lawsuits. Self-driving cars are another type of decision support AI that really and truly require explainability. So in general, if we want AI systems and models to make sensible decisions, we need to ensure the following criteria are followed during development. So that could be the system requirements, how we expect the system to work, how we expect the system to make decisions, and how we actually develop and train those models based on data sets. So we need to be able to explain and gain transparency in an AI model. We need to be able to understand the decision-making process. We need to be able to understand the scenarios when the system can work and even when the system can fail. And finally, we need to be able to determine why the system is making an error. So we need to understand that it is making an error and then why it's making that error. Now that's a nice example from the husky dogs, and the tank example. We need to understand why it was making the error, what was happening in the model. So in industries such as finance, healthcare and law, it is essential to audit the decision-making process. And we need to be able to ensure that it is not discriminating or violating any laws. So going back to our current research on detecting fraud in insurance claims calls, what we are working on amongst a set of partners is coming together in a product called Lexical. So let's look at how it actually works. Before we do that, actually, let's have a think. If we were to use a simple keyword spotting approach to identify each behavioural feature from automatically transcribed speech of the insurance claims calls. So that's, we take the calls, we look at the transcript and we pick out simple keywords, simple keyword spotting. What would actually happen is it would not be very accurate and would actually produce a considerable amount of false positive results, where the system would identify deceptive behaviour in many cases where it should not have. And that is a risk that features relating to the mental health of the caller may be overlooked and poor agent performance masked by such an approach. So we need to move beyond simple keyword spotting. We need something more complex to look at the context of why the person is saying that or how they're saying something. So to deal with this, we have been developing models using state-of-the-art machine learning and deep learning approaches to achieve more consistent and effective results. A combination of different linguistic markers present in the telephone conversation is considered as a strong indication of deception. And this is being considered in the decision-making element of our system. See the decision engine component here, which I will talk about next. For this, we are developing mathematical models to evaluate the rate of appropriately detected linguistic markers and their proximity to one another in the telephone conversation. So apart from linguistic markers, there are many other features which we are considering be very effective for detecting deception. And this can include repetitive speech, where people keep repeating themselves or repeating phrases, or acoustic features such as the pitch, the response latency. How long does it take them to respond? Do they respond very quickly? Do they respond very slowly? Is this out of sync with their normal speech pattern, their speech tempo and their vocal stress? So all of these different components or features of the way people speak and what they're speaking, we are investigating. So looking at the diagram of the system pipeline, the insurance claimant is in a call with the agent. We can see at the beginning. Okay. This audio is recorded and processed by an automatic speech recognition system to produce a transcript of the call. So the transcript is basically a written text document of everything that was said in the call. The technology we have developed now identifies specific markers in the transcript. There are a range of different types of markers. Again, we've got linguistic markers, which involve the use of specific words and phrases. We look at temporal markers, involving variations in time-based measures, for example, measuring how fast somebody is speaking or how slowly they respond to a question. Emotional markers are looking to measure the sentiment of the responses, while acoustic markers measure the speech features such as pitch, volume, etc. After all the relevant markers have been mined from the transcript, and not only have they been mined based on keyword detection, we've been looking at mining them in the context of the conversation. The decision engine component, down here, identifies significant clusters of markers that trigger the system to raise an alert. This alert can be used in real time to inform the agent while they're speaking with an insurance claim applicant, or it can be used post-call to investigate potential suspicious calls in a batch mode. Okay, let's have another look at the decision engine. So this is an overall diagram of the decision engine that we have developed. And we can see that the input is a transcript, so that's a text document of the telephone conversation between an agent and an insurance claimant. And at the output, we have a deception score. Is this suspicious or not? Remember, this is decision support. We're trying to help the agent or the insurance company decide how suspicious or not individual calls are. So, how does it work again? Once the different markers present in the speech have been detected, we now need to identify clusters of these detected markers, as this points to areas of sensitivity in the insurance claim call interaction. The decision engine makes use of this information to produce a deception score. Excuse me. The weighting of the markers, so all the different markers that were detected, the weighting of those markers in combination and in proximity with one another is learned by training the model on real-world examples of deceptive speech in known fraud insurance claims calls. And at the output then we get a deceptive score and an identification of areas of sensitivity within the insurance claim call, which would then be followed up by the agent in the online setting in the real world call or by an investigation team post-call. In this slide, we can see a real-world conversation between an insurance claimant and agent. All personal information has been redacted. We have highlighted the set of linguistic markers which have been detected in this audio transcript. These are color-coded, so we can see red ones have been detected, and this is a linguistic marker called negation. Green one has been detected, this is called disfluency. Blue one has been detected, and this is an explainer. So in this case, the linguistic markers have all been detected, and we can visualize this. We can see that some of the utterances do not have any linguistic markers present. Some of the utterances have 1 to 2 linguistic markers present, but one of the caller's utterances has been color-coded to show the presence of multiple linguistic markers. And at a glance, this appears to be an area of sensitivity. Why are there so many markers in one particular utterance? So once these markers have been detected in the transcript, this information is sent to the decision engine, and we can see the output of that scoring system in the next slide. So here again we have the same transcript from before, but now we're looking at marking up the decision score. So we took the linguistic markers that were detected previously, we fed them into the decision engine, and now we see an output. The decision engine has produced a deception score for each utterance. For the caller only, we're not looking to analyse the agent. And the scoring ranges between 0 to 1, 1 being highly sensitive. This is a clear example of an attempted account takeover if you read through the actual transcript, which our system has automatically detected. The visualization is pretty clear. The sensitive text is highlighted and the overall utterance in red received a score of 0.997, extremely high. For those of you in the know, this is an obvious example of an account takeover, but given the issue of burnout within insurance agents, such a system as this will be invaluable for prompting the agent or follow-up investigation teams to specific areas of sensitivity within the insurance calls. Going back to our explainable ethos when developing AI systems, we can see here that we have not just developed a black box system. Our system not only produces a decision from the deep learning based decision engine, but we also have a clear breakdown of the elements which led to that decision, those being the different linguistic markers detected seen on the previous slide. And this innately makes the system GDPR compliant as it preserves an audit trail of system decision making. We're currently about to start a proof of concept with an American insurance company, and we've recently filed a patent on the overall system. And while this project exists to serve the insurance claims calls use case, the scope of the capability in development would also apply to other areas. It could significantly improve operational efficiency in response to calls to the emergency services. The insight mined from calls made to the emergency services, both of genuine and malicious nature, can be used to develop an AI-based system which will inform and support decision making in a transparent and ethical manner, resulting in the appropriate deployment of resources on a case-by-case basis. The impact of such a system would be felt by the emergency services in reduced costs and risk, while the general public would experience improved services. I'm an academic. I'm based at the University of East London, and as such we have also published research papers on aspects of this work. You can see some here. One has been presented at Interspeech, which is about sentiment classification, and the other was at Europe's, and that was last year. So I want to wrap up now, and I hope that you have enjoyed this session where I have presented our work in developing an explainable deep learning based decision support system for tackling the huge problem of detecting fraud in insurance claims calls. If you do have any questions, I'm available to answer them now. Thank you.